My name is Omar Khader. I am groundwater modeler with Aquanty, and I'm going to present today in behalf of Steve Fry. Um, the topic today will be about modeling groundwater discharge to surface water receptors across Southern Ontario. Um, um, Shout out to all the colleagues shown on the slides that helped in this project. For this one, we started by building and testing 13 fully integrated groundwater surface water models for multi-watershed nutrient studies. These site scale models are small, but it's comparative to other scales that we are going to talk on to these slides. They are still within tens of kilometers of area. When we built these models, we then simulated groundwater flow paths and the dynamic behavior of groundwater flow discharge to mainly streams or other surface water receptors. When we compared these models, we compared different spatial resolution. So we have a regional scale model that we downscaled into watershed models and then site scale models. So we try to compare the base flow index, the groundwater discharge at different scales, trying to show the effect of these resolutions on groundwater discharge. For model validation, we compared the model results to collected values or collected observations from BGMN and from MWNS. The tool we used to do our modeling is Hydrogeosphere. Hydrogeosphere is a fully integrated surface water groundwater model that can simulate the hydrologic cycle. You force the model using precipitation and snow melt and potentially evapotranspiration, and the model will have surface domain which will simulate surface storage, surface runoff, and the surface domain will be fully coupled to a porous media domain that will simulate groundwater flow, infiltration, and discharge. The figure on the right is showing like a small example of how HGS works. This is like a simple one 3D surface domain and subsurface domain. You can see surface runoff going through the overland domain and accumulating into potholes, and then you can see the infiltration going down into heterogeneous, where you have different K layers, and also you have some fractures implemented in the model. So it shows you like the full work of HGS from surface flow to subsurface flow. So for this project, we already built complete Southern Ontario model. This was built based on a 3D geological model developed by Geological Survey of Canada. And we used these layers to build our subsurface model, and also including, so it includes bedrock layers and quaternary layers, and we added soil layers from Soil Survey of Canada. So we have a full model starting from the surface and going up to the Cambrian. This model includes approximately about 20 layers. And I think this model is available through Geological Survey of Canada, the report and the model itself, I think. And from this model, we build nested models. So we build two different scales. The first scale is, we call it the watershed scale model. And these models vary from 3,500 square kilometer to about 12,500 square kilometer. And it covers the whole Southern Ontario. And from this model also, we built 11 site scale nested model. We call them the site scale model, and they vary from 20 to 70 square kilometer. They will carry the same data from this regional scale Southern Ontario model. This is an example of the first scale, which we call the watershed scale model. I'm showing here two examples, the Aquanty region watershed model and the long point model. In this model, we increased, the good thing about the initial model is that we increased resolution, so the mesh is more refined, and we added more streams. So for the regional model, we carried stroller order 3 and larger, just to keep the node counts in limit, so the model will run quick enough. But for the watershed scale model, we increased to stroller order 2 and above, high resolution. In later slides, I will show like a side-by-side comparison of these mesh scales. This map shows the boundary for all 13 watershed models. You can see it covers the whole Southern Ontario model. The stream shown here is stroller order 3 and above. So these stream orders are the one used in the regional model. It's shown here on the scale. On the watershed scale models. It will be hard to see. It will be super refined to see like stroller order 2 or 1 in this case. But yeah, you can see even the regional scale model carries significant amount of streams. These slides show the boundaries for the site scale models. We have 11. They vary in location within Southern Ontario. From the east, we have Gage Creek. From the west, we have Big Creek. We have Venison Creek to the south, and up till the Maitland River site scale model. We have 11 of these scale models. These scale models are more refined, and they carry stroller order up to stroller order 1. So all vector network, stroller and vector network available are implemented in these site scale models. This show how we built the multi-watershed nutrient models. The site scale models show this top left shows a mesh, highly refined mesh, carry stroller order 1 and above. For this one, since we have more resolution, we updated some of the data. So for DEM, we went to the Ontario DEM, which is resolution of 2 meters. So we went with a more refined DEM since we have higher node counts. We use the detailed soil survey of Canada, and the land cover is based on the North America land cover change monitoring system. This is a harmonized data for whole of North America, and it carry a resolution of 30 meters. And I think this version is a 2015 version. And on the slide on the side, you can see all the model layers starting from the bottom up, and so the bedrock is still based on the regional model, which is based on the 3D geological model, which carries the bedrock and the superficial layers, and then we have the soil on top from the detailed soil survey of Canada. We run this model using rainfall and PET. And on these slides, you can see the dynamic of fluid exchange or flux exchange for these models. You can see the date here changing, and you can see the amount of water infiltrating into the soil or exfiltrating into the streams, like groundwater discharge and recharge over this period. The other one on the side is showing only the portion of water discharging from the groundwater into the stream network. You can see it's dynamic. It's based on a bunch of parameters, including rain, evapotranspiration, surface storage, and groundwater storage. I'm going to show 3 examples of the site scale models here, showing results and calculations we've done. First model we look at is Nanticoke Creek, 22 square kilometers. You can see on the left bottom the 3D model, and showing on the top the elevation, surface elevation for this model. We took this model, we calibrate this model to runoff or stream flow coming from the outlet of the site scale model. You can see an edge side cliff of 0.56 and a bit higher bias to about 20%, but we were able to capture somehow the response, close enough the response of this model. Still, we are using graded data for rain and precipitation, so there is some uncertainty in the forcing data, but overall the model performance were good. On the bottom right figure, we can see the outlet flow coming out from the model, and groundwater discharge, and the calculation of base flow index, which is a percent of groundwater contribution to the total flow coming out of the model. And you can see that the groundwater contribution in a model like this one, in average range about 23%. So quarter of the flow coming out is coming from groundwater discharge. A second model here is Big Creek. This one is to the west, and in this area we have like a thick till layers. So the subsurface is a bit low conductivity, and you can see from the topography here it's almost flat. If we look at the hydrograph, we were able to capture most of the peaks, Nash set cliff of 0.71 and a percent bias of -7%. The model performance is acceptable, and if we look at this example, we would expect that the base flow index to be a bit lower. You can see like flow coming out, groundwater contribution, and the base flow index in this case is 0.02. So we have about 2% of the water coming out is from groundwater contribution. We have a third example here, which is Venison Creek. This one here to the south, about 44 square kilometers. You can look, we can see some topography here. And if we look at the model performance, the calibration, we have a Nash set cliff of 0.64 and a small bias of 7%. Model capture nicely some of the peaks. Still, we have some uncertainty in the forcing data, but overall the model performance is great. We look in this one, this is to the high side. We look at outlet flow for the model or surface runoff, and you look at the base flow index, and about 67% of the water going through like coming through the outlet is from groundwater contribution. We arrange here the 11 site scale model, and we show the range of base flow index, which range from 67% to about 0%. And mainly what affecting this percentage is hydraulic conductivity for the active layers, and the topography are the main contributor to which we found that affects how much groundwater contribution we can have. For the next slides, we will show a comparison between different scales, or like the effect of scale resolution on um, on groundwater discharge. And you can see here the difference in mesh between the site scale model, which carries roller order 1. Element size is about 100 meters away from streams, and for elements close to the streams, we do more refinement, where we know that lots of activities or action will happen close to the stream. So goes down to about 50 meters. For the watershed scale model, it carries roller order 2 and above. 600 meters is the edge length away from the streams. Also more refined at the streams of about 200 meters. You look at the regional scale model, and it carries roller order 3, so it's only one main stream moving through this area, and the edge length is about 1.5 kilometers away from streams and half a kilometer close to the streams. So very diverse spatial resolution here. And the next we will see what is the groundwater discharge coming out of these 3 models. You can see the effect of different resolution through these models. Base flow index calculated through the multi-watershed, the site scale model shows about 23%. Through the watershed scale model is showing a base flow index of 0.75. You can see the matching between areas where it shows higher groundwater discharge is matching in these models with different accuracy. For the high resolution model, you can see showing about 50%, showing also closer areas where the groundwater contribution will occur. This one will have a different scale, a bit different scales, just to show, trying to capture, like chart should show different colors, or like the contrast to give you like an idea where this model are showing. Have another model here, which is Big Creek model. Can see here where the contribution of groundwater occur. We have a base flow index of 2%. Same here, when you look, it show you close areas, good correlation, and it's the percent is below 1% here, so it's a tiny contribution. This one we couldn't capture where the groundwater contribution occur at for this model at that scale. For summary, regional models are very useful in constructing nested model. So we were able to use one regional model to create in total about 24 different models using different scales. So it makes the process of creating nested models for area of interest much easier. So the groundwater contribution to surface water is highly variable across sites and seasons. So you can see at these different models showing ranges from close to like 70% groundwater contribution to about close to less than 1% in some of these models. And also through the season, this percent also changes. Coarse model and large scale models can provide reasonable estimate. So we still can see in the regional models, most of the areas that will represent an area of interest for groundwater contribution, and these areas we can go and build like a high resolution to try to figure out exactly the amount of groundwater contribution in these areas. They lack the spatial fidelity of the high resolution small scale models. So, and then we compared the base flow index from the correlation between site scale and watershed scale base flow index, and was about 3.3. And between watershed scale model and the regional scale model was about 0.32, and the R square between the site scale and the regional scale is about 0.12. So we have good correlation between each scale and the scale below it. And thanks. This is the full presentation.